In networking, messages do not exist forever. They are created, transmitted, processed, and eventually disappear. This temporary existence is called message lifetime. Message lifetime describes how long a message remains valid, relevant, or retrievable within a system or network. It is not just about transmission time. It is about the entire lifespan of a message, from creation to expiration. Understanding message lifetime helps explain how networks manage memory, reliability, retries, and system behavior under failure. So what is message lifetime in networking? Message lifetime is the duration during which a message exists somewhere in the system. This could be inside a sender's buffer, inside the network, inside a queue, or inside a receiver waiting to be processed. Eventually, every message reaches the end of its lifetime. It is delivered, discarded, overwritten, expired, or forgotten. Networks are not designed to remember messages forever. They are designed to move messages and then let them go. You can think of message lifetime like a shipping label on a package that eventually expires. If the package cannot be delivered within a certain time, the system stops trying. The message is no longer useful. Now let's look at how message lifetime works in practice. When an endpoint creates a message, it enters a transmission buffer. From there, it travels through the network toward its destination. During this time, the message may exist in multiple places: in network device queues, in transport layer buffers, in operating system memory, or in application-level queues. Each location temporarily stores the message. But none of these locations store messages permanently. Most protocols define limits on how long a message may live. For example, IP packets use a time to live, or TTL field to prevent packets from circulating forever. Each network hop reduces the TTL value. When it reaches 0, the packet is discarded. This is a direct example of message lifetime control. Transport protocols also manage lifetime. A TTP segment stored for retransmission will only be kept for a limited time. After enough retries or timeout events, the system gives up. Message queues do the same thing. Queued messages often have expiration times. Old messages are removed automatically. Applications may also enforce lifetime rules. A request that arrives too late may be ignored. A response that arrives after a timeout may be discarded. This shows an important principle. Message lifetime is enforced at multiple layers. Why does message lifetime matter? Because messages consume resources. Memory is limited. Buffers are limited. Queue space is limited. If messages never expired, systems would eventually run out of capacity. Message lifetime also protects systems from instability. Imagine packets looping forever in a routing error. Without lifetime limits, the network could collapse under endless traffic. TTL exists specifically to prevent this. Message lifetime also defines relevance. A delayed message may no longer be useful. A response that arrives after a retry may conflict with newer state. Distributed systems depend on time-sensitive communication. Old messages can be dangerous. This is why systems treat stale messages carefully. Now let's look at the key characteristics of message lifetime. First, message lifetime is bounded. Messages always have an expiration condition, even if it is implicit. Second, message lifetime is layered. Different system components enforce different lifetime limits. Third, message lifetime is resource-driven. Buffers, queues, and retry policies determine how long messages persist. Fourth, message lifetime is context-dependent. A message may be valid in one moment and useless in the next. Fifth, message lifetime interacts with timeouts and retries. Timeouts define when a message is considered too old. Retries create new messages with new lifetimes. This interaction is fundamental to reliable communication. Message lifetime also influences system design. Short lifetimes reduce memory usage, but increase the risk of dropped communication. Long lifetimes improve resilience, but increase resource consumption. There is always a trade-off. Real systems choose lifetime values carefully. Streaming systems use very short lifetimes. Email systems use long ones. Message queues often allow configurable expiration. Each system balances reliability, timeliness, and resource limits differently. Message lifetime also affects debugging and observability. A message that has expired leaves no trace. From the outside, it looks like it never existed. This can make failures difficult to understand. Finally, message lifetime reminds us of something fundamental about networking. Messages are temporary carriers of intent. They exist only long enough to move information between endpoints. Once that purpose is fulfilled or no longer possible, the message disappears. Networking is not about storing communication. It is about moving communication through time. Messages are created, messages travel, messages expire. That entire journey is message lifetime. And understanding message lifetime helps explain why networks remain stable, efficient, and scalable, even when communication is imperfect. That is message lifetime.